welcome everyone to join our session. Hope you guys already enjoyed your lunch. So today we'd love to present our work on Stable Diffusion pre-training on billions of images with Ray. My name is Yuxuan. I'm a software engineer at Anyscale, working on building distributed training infrastructure on top of Ray. I'm one of the maintainers of RayTrain and RayTune library. And this is my colleague, Hao.
Good afternoon, everyone. My name is Hao. I'm also from Anyscale, currently mainly focusing on Ray data. So I have been working on Ray since the beginning of this project. So prior to Anyscale, I work at the Ant Group. Ant Group is the first company that starts adopting Ray in massive production jobs. So I was leading the Ray team there, responsible for managing and improving Ray and supporting other teams to build variety types of applications, distributed applications on top of Ray. And prior to that, I work at Facebook on some Instagram web efficiency stuff.
Thank you, Hao. Cool. So before we dive into the technical detail, I'd love to give everyone a short overview of our project. So here, we propose a pipeline that pre-trained the Stable Diffusion V2 model on over 2 billion images for less than $40,000. To achieve this cost efficiency, we've adopted Ray data and RayTrain for both data preprocessing and distributed training. So with Ray data, we can efficiently preprocess large-scale datasets with streaming execution, utilize heterogeneous resources. With RayTrain, we can leverage its scalable and fault-tolerant training features, and also integrate with infrastructure and algorithm optimizations that collectively improve the overall throughput by 3 times. And for the following section, I will first discuss our pre-training workload, the backgrounds and challenges, and I will hand it over to Hao to discuss how to actually build this scalable data pipeline with Ray data. And finally, I will discuss how we do efficient distributed training with RayTrain. Cool. And the first question, why we need to pre-train Stable Diffusion from scratch instead of like fine-tuning from the open source the checkpoints, the open source modelways. So the biggest concern here is the AI safety issue. So as a background, the original Stable Diffusion model is pre-trained on this Line 5B dataset, which is the open sourced web crawl dataset. However, it doesn't have rigorous filtering that it might contain some illegal or copyrighted images in this dataset. So the model trained on this dataset is also prone to generate the image with illegal contents, like at the right-hand side shows. So, however, if we can control our pre-training pipeline, we can use the carefully curated image datasets that is more safer for commercial use. And also, you can train your proprietary model that have higher image generation quality, for example, higher resolution, or also you can support multi-language support, which is not achievable through fine-tuning only on small datasets. So here I shows the overall architecture of Stable Diffusion model. It contains 3 submodules: the VAE image encoder, text encoder, and UNet model. The VAE encoder and text encoder will encode your input image and your text prompt into image latents and text embedding. There's a noisy scheduler that adds some noise into the image latents, and these two got input into the UNet model. The UNet model will learn the diffusion process by predicting the noise you added to the image latents, and then calculate the MIC loss as the training signal. And this overall data flow looks pretty straightforward. However, when we move to large-scale pre-training, there are the following challenges. The first part of challenges is about data preprocessing. So firstly, we have a really large-scale data set that contains 2 billion images, and the preprocessed image latents contains about several hundred terabytes of data. And secondly, we have complex and heavy preprocessing logics that involves both CPU-intensive and GPU-intensive workloads. How to effectively coordinate and launch these different tasks on correct devices to maximize your cluster's utilization, that is another challenge. On the training side, Stable Diffusion pre-training is a learning job that costs more than 30,000 A100 hours. So the node failure and software failure is is pretty common. So we need an efficient way to do fault-tolerant training to minimize your training progress loss. And also, like, optimize your training loop to maximize the GPU utilization can, like, reduce the time on model training, thus save your money on this precious A100 instance. So to address these challenges, our solution is to use Ray. So what is Ray? Ray is an open source distributed framework that helps you to scale your Python workload, especially your AI workload. It is created by Berkeley Rice Lab in 2016, and 3 years later, the creator of Ray founded Anyscale, where we provide a fully managed service of Ray cluster and help users to easily deploy and develop their ML models. And Ray has been widely adopted during the past few years with both open source users and also some famous companies in the industry. So next, I will hand it over to Hal to discuss how to use Ray data to implement a scalable preprocessing pipeline.
Okay, thanks, Yunshen. In the next section, I'm going to talk about how we handle the challenges in data processing with Ray data. So first of all, let's take a look at, without using Ray data, how do we typically implement this data processing pipeline? So to achieve data parallel chaining, we need multiple A100 nodes, and on each node, we use torch data loader to ingest the data, and then apply a bunch of preprocessing functions sequentially, and then feed the data into the model chaining. So all of this happens on the same A100 node. So this architecture is typically fine for normal workloads, but in the Stable Diffusion case, so we have a bunch of complex data preprocessing functions. For example, we need to transform the images, we need to tokenize the text captions, and then do encoding for both the image and text. So we can notice that the first two operations only need CPUs, and the second two encoding operations, they do need GPUs, but they don't need high-end GPUs such as A100s. So the chart on the right side is an experiment we did. So if we put both the encoding and the model chaining on the same A100 GPU, we can see that most of the time, the GPU RAM utilization is very low. It's only like about 25%. So basically, with this approach, we are not fully utilizing the power of A100s. So a straightforward solution to handle this, to avoid the data processing bottleneck, is to decouple the data processing with the chaining. We can use an offline job to like preprocess the data and save the data back to cloud storage. And then in the chaining job, we can directly ingest the data and feed the data into the A100 for chaining. So by decoupling them for the chaining job, we can make the A100s dedicated for the model chaining. So to implement such a data processing pipeline at this scale is not an easy task. So first of all, we have billions of images to handle, whose size is more than 100 terabytes of data. We need a system that can efficiently scale to this size without any stability issues. And secondly, we want to fully saturate our GPUs to get the best performance. And thirdly, we need a system that is resilient to failures, because the job can take multiple days or weeks to finish. We don't want the job to crash in the middle due to a random failure. So next, let's see how we use Ray data to solve these issues. So first of all, let me give a very quick introduction about what Ray data is. Ray data is a scalable data processing library for machine learning workloads built on top of Ray. So we particularly optimize Ray data for two major scenarios. One is offline batch inference. The typical use case includes, for example, image, video, audio inference, embedding generation, LLM batch inference, and so on. And in our case, this Stable Diffusion offline data pipeline is a typical offline batch inference job. And the second scenario is for chaining ingestion. Basically, you can use read data as a more scalable and performant replacement for Torch or TensorFlow data loader to do the data loading and preprocessing for your chaining job. We will take a closer look at later for these parts later. Okay, now let's take a look at this code example to see how we implement the offline data pipeline with read data. So first of all, we use this read parquet function to create a data set. Basically, this data set will load the data from L3, load your parquet data from L3, and the next step, we define such a function and pass it to the ds.map API. Basically, by doing this, we tell read data to apply the transformation, the image transformation and text tokenization for each row in this data set. And thirdly, we define this SD latent encoder class and pass it to the ds.map batches API. So this tells read data to apply the encoding logic to the data set. There are some differences. If you compare this step with the previous step, there are some differences. So first of all, we use map batches instead of map because we want to apply the transformation to a batch of data each time because the GPU operations can be vectorized. And we use a class instead of a function. This allows us to only load and cache the model once in the constructor of this class. And more importantly, you may notice that we can set number GPUs to 1 to this map batches operator. So basically, this will tell read data that each task of this operator will use 1 GPU. In the previous operator, we didn't set that. So by default, it will use 1 CPU. And lastly, we use this write parquet function to write the data to L3, back to L3. So with this, a few lines of code, we can easily implement this pipeline with read data. And then next, let me explain what's happening under the hood that makes read data more scalable and performant. So first of all, during the entire pipeline, everything is streaming, so including all the reading, writing, and the transformation, everything's streaming. So this allows read data to scale to petabyte scale of data without any stability issues. And secondly, as I mentioned before, read data support heterogeneous resource requirements. You can specify CPU or GPU resources for different types of tasks. Then read data can schedule them accordingly on different hardwares. And third, read data is fault tolerant. And also, read data support a large variety of data sources and formats that are commonly used in machine learning jobs. And last but not least, read data is Python native, and you can seamlessly integrate read data with other machine learning libraries. So among all these features, the heterogeneous resource scheduling is the most unique feature that makes read data really stand out among other solutions. Now let me use a diagram to explain why this matters. So this diagram shows the data pipeline we have for this offline job. So first of all, data can stream the data across the entire pipeline, and we use read object store to cache and buffer the intermediate data. So read object store is a distributed data storage that uses shared memory to allow sharing data among different processes in the same cluster. And the read data can schedule the CPU tasks on CPUs, GPU tasks on GPUs. And more importantly, read data allows the operators to adjust their parallelisms independently and dynamically. So for example, if your GPU operation is undersaturated, so read data will simply schedule more CPU tasks to increase your saturation of the GPU operation. So then let's look at some benchmark results. So first, we can get a linear throughput. The throughput can scale linearly while we add more nodes. And also we can get a very nearly full GPU utilization across the entire job, thanks to the heterogeneous resource scheduling ability. And by introducing this offline pipeline, we can get rid of the data processing bottleneck in your training job. So by doing so, we improve the data throughput by 45%. But however, like sometimes this offline processing approach is not always the best solution. So for example, sometimes you may want to do some experiments on different types of preprocessing logics. You don't want to wait for the entire data set to be processed before kicking off your training job each time. And also sometimes you may want to apply like dynamic like processing logics across different epochs. And in this case, the offline solution is also not the best option. So the question we want to answer is, how can we achieve efficient online processing without blocking the A100 CPUs? So as I mentioned before, there's another scenario for read data is for chaining ingestion. And in this slide, I'm going to talk about how we use read data to implement this online processing pipeline. First, we can define the processing pipeline. We use exactly the same code we used before for the offline job. And then we create two data sets. So one for the chaining, one for the validation. And to implement data parallel chaining, so typically you need to like partition your data ahead of time before kicking off your training job. But with read data, we can automatically do this for you. It's happening. So the data will shard the data under the hood dynamically at runtime. So you don't need to do it manually. And then in your training function, you simply just you can use this API to get the shard that is assigned to this training worker and and iterate the data and feed the data into your model as you normally do with your torch data loader. And also, it's worth mentioning that, so in terms of the heterogeneous resource requirements, besides supporting CPU and GPU, read data can also support different types of GPU. Okay, so this diagram captures the overall architecture of using read data for the online data pipeline. So you can see we have like 3 groups of tasks here. So for the image transform text tokenize, they only need a CPU, we schedule them to CPUs. And for the encodings, we schedule them to A10G GPUs. And for the training workers, they are scheduled to A100s. So basically, with this architecture, read data can also scale up each group of tasks like individually. So we can make sure that both the A10G and A100 GPUs are always fully saturated. Okay, we also did some benchmark results for this online pipeline. So first of all, we can see that the first experiment is that if we fix the number of A100s, the training throughput can scale linearly while we add more A10G nodes. And the table on the right side shows some comparison of some key metrics between using read data versus using torch data loader for the online preprocessing job. So for both setup, we use 38 A100s on 4 P4DE nodes. And for the read data job, we add 40 additional A10G nodes. So we can see, so by using read data, we can increase the throughput by 45%, which is the same as the offline job. And we decrease the total training time by 31% and reduce the cost by 10%. Okay, I think that's what we have, the problems we solved for data processing. Now I will hand back over to Yunshen to talk about the challenges in training.
Cool. Thank you, Hao, for sharing the data processing pipeline. Next, I'd love to share about our design for the training pipeline. First of all, we use RayTrain to implement this data pipeline, this training pipeline. So RayTrain is a scalable ML library that can help you to easily scale your single machine training code to a cluster of machines with minimum code change. So as shown on the right-hand side is the skeleton of your code. Basically, you need to define your training function, which is just your normal PyTorch or Lightning or Hugging Face training code. And you have to Also define a scaling config to specify the number of workers, number of GPUs you use for this distributed training. And then you create a torch trainer and call trainer.fit. And this, at the left-hand side, shows the torch trainer will help you to launch the training function as a remote function on the correct devices. And you don't have to worry about the resource scheduling or orchestration under the hood. Like the training just happens as if you are running your training code on a single laptop. And moreover, like ray training has wide integration with ecosystem. We support famous ML frameworks like PyTorch, Lightning, Hugging Face, TensorFlow, and also Ray itself is compatible with different cloud providers like AWS, GCP, Azure, and also can run on some cluster management orchestration layer like Kubernetes. Therefore, like you can run your ray train workload as long as you have a ray cluster that has started on different underlying infrastructure. And let me share a more concrete example of how to implement a training function with ray train. So as the left-hand side shows, this is what we normally write when you do like run distributed training with torch run or other launcher. So you have to manually set up these environment variables and wrap your model with DDP and set up distributed samplers and also like move the batches to GPU like after you fetch the batches from PyTorch data loader. With retrain, you just need to wrap your model and data loader with 2 utilities. And you don't have to worry about all this tedious stuff, and which can simplify your code pretty much. And similar things for PyTorch Lightning, you just replace the DDP strategy and Lightning environment with our like Ray-provided utilities. And no other changes is required for your model and training strategies. And besides this, what are the key features that are important for Stable Diffusion pre-training? I'll go over these 3 one by one. First, let's take a look at the fault-tolerant training. So assume that we save a checkpoint for every n steps, and there could be some failures. For example, node preemption or just node died for some reason. And retrain will help you to automatically detect these node failures and restore training from the latest checkpoints. Let's take node preemption as example. If you're using spot instance, one of the node get preempted, and ray cluster will detect, okay, this node died, and it will trigger the autoscaler to scale up to the original size of your cluster. And retrain then fetch the latest checkpoint from cluster storage, for example, S3 buckets, and then like your model will load this checkpoint and resume from latest one, the previous checkpoint step so that it can minimize your training progress loss. Apart from this auto restoration logic, we also provide efficient distributed checkpointing. So when you're training, especially large models, checkpointing could be a big issue. For example, if you want to save checkpoint every 30 minutes, but saving checkpoints takes 10 minutes, that is totally unacceptable. Like your training efficiency will decrease by 1/3. So here, Raytrain provides this way to independently upload your checkpoint shard from each worker. For example, if you're using FSDP, fully shard mode, each worker will have a part of the model parameters saved locally. And Raytrain will help you to synchronize this checkpoint concurrently to cloud storage that can minimize your time on checkpointing. Okay, like with efficient checkpointing and restoration, we've minimized the cost that's happening during the failure recovery phase. And next, I'd love to talk about how we improve the training speed itself. So Stable Diffusion training involves a large gradient syncing. Like if you're using DDP, for every training step, you have to aggregate all the gradients from all the workers, right? So the communication, internal communication becomes a bottleneck. So here we use EFA, which is the network layer provided by AWS that provide high bandwidth, low latency interconnect comparing with normal TCP transport. As we show in the right-hand side, EFA provides us with more than 2.5 times speed up over the overall training throughput. Apart from the network layer, we also adopt this FSDP strategy to help you efficiently do this large-scale training more efficiently. So the problem for DDP is that training on DDP requires each worker have a full copy of your model state. The model state here refers to your model weights, the gradients, and your optimizer states. And so that you cannot accommodate a large batch on your, for example, A100s. And also it requires the full checkpoint, full gradient syncing. So FSDP, to resolve this problem, it shards the model state on each worker so that each worker only have partial weights and gradients. So during forward pass on the current layer, it will gather the required parameters for this layer, do the forward pass, and then discard these layers so that you can imagine it will have much lower GPU memory requirements. And also, it's reduced the needs of full gradient syncing because each worker only needs a gradient for its own weights shards. So by combining these optimizations, including EFA, FSDP, and also torch compile, we are able to get approximately 3 times speed up over the baseline method using DDP. And here are the results. We finished training on AWS with P40E instance. We use a global batch size of 4,096, and it costs 13,000 A100 hours, which by calculation is under $40,000 with 1-year reservation instances. And more details, I'll share a QR code for our blog post. Has more detailed analysis. And yeah, takeaways. So throughout this large-scale pre-training, we've used the following 3 tools and platforms. The first is RateData. So RateData supports streaming execution, leveraging heterogeneous resource like different GPU types and GPU and CPU to achieve a more efficient preprocessing utilization. And also it supports fault tolerance and dynamic data sharding that can help you to reduce the complexity to develop your training pipeline. Secondly, retrain. We use retrain for efficient and fault tolerance large-scale training. So retrain provides a simple interface for you to migrate your original PyTorch code into a distributed fashion. And it has great framework ecosystem integrations that can make your user experience much more easier. And it also supports fault-hardened training to reduce the cost is spent on fault failure recovery. And lastly, all this experiment is done on the AnyScale platform. So AnyScale platform is the best place to run your rig workloads. So basically, we have a fully managed rig service plus proprietary features over the normal open source rig, so which can boost your training efficiency even more. Also, the infrastructure and features in this AnyScale platform can help you to accelerate the ML development and deployment cycles. And yeah, that's all the things that we'd love to share today. And here are the QR code. At left-hand side is our AnyScale platform. Feel free to register it and play around with the workspace templates. It has different workload, for example, model training, large language model, and diffusion model, and also serving, and also data preprocessing. And we have some free credit for that. And at the right-hand side is our blog posts that have more detailed analysis of how we design this pre-training pipeline and what's the performance comparing with the different baseline methods and how it scales across the large cluster.
Thank you guys so much for your time.
Thank you, everyone.